Okay, so welcome back once again. I don't know how because this meeting ended maybe in half an hour.
मतलब
Hello.
मेरा भी ऑन
So you are finding the dimensions. Still few people are joining here. So are you finding dimensions now? So when you are ready with the dimensions, let me know. Okay. So is there anybody who has found out all the dimensions of the gear and pinion? If you are ready with the answers, I will just run the code and we'll cross verify the answers. Still three people are waiting. Well, many of you are writing P in the chat box now. Don't do that. I will tell you when to do that. Okay, don't write P in the chat box. Or else then I will stop the chat box and I will just make it active whenever I want, as the other professors do. Okay, so are you ready with the dimensions? Or you require some more time? Well, is there anybody who has come up with all the calculations as far as the dimensions of the gears are concerned? Obed Sheikh, you need to unmute yourself, mute yourself. Okay, if you are telling answers, that's fine. Otherwise, mute yourself. Obed, are you listening to me? Can anybody tell Obed to mute himself, or I'll just do that from here. Okay, so anybody? Are you ready with the answers? Come on, guys. See, because of this virtual platform, we are a bit faster. If it had been in the class, it would have been much slower actually. Okay, so there is some issue with my video also. Let me check. Now it's clear. Yeah. Acha, so I need to share the screen. I have not shared the screen. Yeah, so these are the dimensions in front of you here. See, there are two columns. This one is for spur gears and this one is for helical gears. Okay, so make use of these relations and find out. Yeah, any answer? Come on. Yeah, Rohan, thank you for that.
Sir,
Yeah, tell me the
I
answers.
have so number of teeth for
Uh,
pigeon 18.
Number of teeth. That Z1 we know, no?
Yeah.
Z1 we know, Z2 we know. Or just what we'll do, because there are many dimensions in this, right?
Yes, sir.
I will just run the that portion of the code, and it will be on the screen. So we will cross verify there, because when my answer is not in front of you, it will be difficult for us to cross verify, because
Yes,
there are
sir.
many dimensions, right? So I will just run that portion of the code now. Okay, so here the step number 6 is dimensions of spur gears. Okay, so I have just mentioned all these dimensions here. Okay, so the code will do that, and it will collect in a table. So I will run till this point, 216. Okay, so let's cross verify our answers. Uh-oh, I committed a mistake. Should be F9. Yeah, so just let's cross verify the answers here. Well,
Yes,
so
sir.
this table shows all the parameters here. So Z1 and Z2, 81, 89, 71. Then we have module 4 millimeters, because this is now change module for to take care of
Yes,
the
sir.
failure in wear strength. Beam face width 40 millimeters. Now all the answers here are in SI units, whenever it is applicable, wherever it is applicable. Okay, so this is the odd. Next one, pitch circle diameters. D1 is 72, rounded off, and D2 is 281. Again, it is rounded off.
Yes, sir.
Then we
Yes, sir.
have this is addendum 4 millimeters. Yep,
Yes,
it
sir.
is HA. Then we have dedendum as 5 millimeters for both gears. This 1 millimeter is
Yes, sir.
clearance.
Yes, sir.
We have tooth thickness
Yes, sir.
Yes,
6.28.
sir.
Then what is this? 1.52.
Yes, sir.
What is that?
Fillet radius.
Yeah, it is fillet radius. Okay, 1.52. It is 0.38 times module. And then we have tip and root diameters for pinion and gear. So 80 millimeters and 289 tip diameters. 62 millimeters and 271 millimeters are the tip and root diameters for the gear. So
Yes,
this
sir.
answers, okay, very good, great. So we have done this portion of the what to say, design. Now next step, up once you have all the dimensions with you, last part of this design is to mention or talk about what would be the construction of the gear, how it is actually manufactured. Okay, so we need to give constructional details, and for that I think again we need to go back to the PPT. I will just share the PPT with you. It should be open, right? Yes. Okay, so we have completed 6 steps, and last step we are now moving on to, so constructional details. Okay, I will go to uh, slideshow. Well, okay, so as far as the constructional details of the gears, we are talking about the spur gears, and it is applicable to helical gears also. Okay, so there are typically three types of gears: small sized, medium sized, and large sized gears. Now we will discuss about the small size gears first. Okay, so which gear is considered as a small size gear? Wait a minute. Okay, so a gear or pinion with root diameter, that is dedendum diameters, which is near or equal to, almost equal to, what is the shaft diameter on which it is going to be mounted. Okay, if it is, they are very close, then we say the gear size is very small, rather than saying very, it is small. Okay, and then what should be the construction, how we are going to mount the gear on this particular shaft. So what is the thumb rule? It says if the diameter of dedendum circle df exceeds the diameter of the shaft ds, okay, at the point where the pinion is fitted on the shaft, if this is less than ds by 2, the pinion is made integral with the shaft. Now, essentially what is meaning of this statement is that if you take the difference of df and ds, what is the diameter of the dedendum circle minus diameter of the shaft, we will find out what is diameter of shaft ds in, and then we will take the difference. If this difference is less than ds by 2, then we will make pinion integral with the shaft. If it is not the case, then we will consider the pinion is made separate from the shaft. Okay, so that is the situation. Now what are the advantages of integral construction? It reduces the amount of machining as well as the cost, because there is no need to machine the keyways to mount or fit gear on the shaft, right? So it reduces cost as well as the machining amount of machining also. And because it is integral, the gear is directly onto the shaft material, as shown in this figure here, the integral gear. Okay, it increases the rigidity of the whole arrangement, and because of this rigidity, it leads to accuracy of the contact also. Okay, but then it is only used for for small size if it satisfies this condition. Otherwise, we will go for a separate pinion and shaft. Okay, so now we'll move on to the medium size gears. So what is meaning of medium size gears? The generally size is considered between 150 to 400 millimeters. Okay, again there may be some variation from this, that's fine. And medium sized gears are generally manufactured by two methodologies or two ways. One is machining from the bar stock, and we have another is forging. Okay, so when can we machine from the bar stock or rolled steel bars? If the addendum circle diameter, that is tip diameter of that particular gear or pinion, is up to 150 millimeters. or less than that. Okay, so in that case we will machine the gear blank, or which is nothing but a flat circular disc from the bar stock, and we will machine on the lathe machines to the size of the gear, and then it will be sent for cutting the teeth by different methods like honing and other things, right? So that is very simple way of doing it. But if the gear size is more than 150 millimeter and it is up to 400 millimeters, we will go for forging. Okay, forging is what is a costly method compared to machining. But if the volume is large, then we can actually go for forging. Volume of the gears which are being manufactured is large, then we can go for forging. Now, you in case of machine design 1, you might have studied what are the design considerations in forging. Okay, let me see what has happened to this. Give me a minute. Okay, I will stop this and restart. Okay. Well, so I was mentioning about the forging, and you have already studied what are the design requirements in forging and design requirements in casting in MD1. So I recommend strongly that you should go back to these sections in MD1 and just go through what are the design considerations for forging and what are the design considerations for casting, because large size gears are manufactured by casting. Okay, so if you just compare machining from bar stock and for with forging, forging has very what to say, many advantages over the machining, but only difficulties with the cost. So essentially, we will go for forging if the volume of gears being manufactured is large. Okay, then only forging will be cost effective. But otherwise, forged components are very strong compared to machine components because of the intact fiber lines. So I will not go into details of this. You just refer to machine design 1 and go through the article on design for forging and design for casting. Okay, so if the gear size is between 150 to 400 millimeters, generally they are made as shown in this figure here, which consists of three sections. One is hub, which is central portion of the gear blank. Then we have web, and then there is a rim. Okay, so on the rim there will be teeth will be cut, and it is a single section actually. Okay, so there are holes which are drilled into the web, and this is done for machining. Fine. So as far as this solid construction is concerned, machine gears, you need to actually remember this figure, cut section of the gear blank, wherein this particular portion shows the gear teeth, then the material over here which is cut, then this is the portion to accommodate the shaft, and if it is made separate from the shaft, then there will be a keyway as shown here. Okay, so these dimensions, primary dimensions you need to mention, and you need to draw this diagram in your answer. As far as the forging and the gears with the size of 150 to 400 millimeters are concerned, you need to draw this diagram, but you can refer data book for this. Let me see in the data book which page it is. Okay, so gears. Okay, proportions of large gears. Here, there we go. Yeah. So this is on page number 8.62. So remember this page number 8.62. Here we see forged cylindrical gear. So straight away we will consider draw this diagram by from this book on this page, and there these dimensions are mentioned. You need to calculate these dimensions and write down there. That's it. Okay, so that is for medium size gears. and the constructional details for large size gears or large diameter gears with large diameter. Again, there are two methodologies here. Up to the gear, if the diameter pitch circle, addendum circle diameter is up to 900 millimeters, then we will go for solid cast gears. So both these gears are manufactured by casting. And then there is if the diameter is above 1000 millimeters, then we will go for rimmed gears. Okay. So what is meaning of solid cast gear and rimmed gears? We will just spend some time on this. Okay, so this particular gear diagram shows cast iron web type gear, wherein this is the side view and this is cut section of the front view. You can see there are two webs in this. Instead of a single web which we saw on the previous slide, here I will just go back. Here we saw the single web here, whereas in this case there are two webs because the large size is large, and this is solid cast gear. Okay, but it is up to size 900 millimeters. If the size is above this or 1000, more than 1000 millimeters, then we will go for something called as rimmed gear. Here in what happens, we will have a blank of cast iron which is cast, and we will have a steel rim. Okay, you can see this diagram here. We will have a steel rim which is press fitted or bolted to the cast iron hub as shown in this case. Okay. If it is press fitted, there will be set screws which will be used here to avoid the relative motion between the rim and the hub during operation. Okay, so these are the different types of constructional details as far as the gears are concerned, and then now we will go for actual calculation of the dimensions. Right. So what is the condition for integral gears? Is there anybody who can tell me? Because we need to calculate now. Are you with me, or just switch on the video and just keep aside? Come on, guys. Okay, so by that time I will so mention P in the chat so that I will save the attendance for this session. So chat is not available or what? Well, anybody can you tell me what is the condition for integral gears or integral construction?
Diameter of dedendum circle minus diameter of shaft. If less than diameter of shaft by 2, then integral.
Yeah, that's fine. Great. Okay, so we'll go and check whether it is the case with us. So here, if you see the code, I will just mention there. So now, see the constructional details. This portion of the code, we will find out these dimensions for constructional details. Okay, so but we need to know what is the diameter of the shaft for this, right? When you find out difference, so we will select some shaft material. Now, if you go to page number 1.10 in data book, go to page number 1.10. That is in materials. So it is about, okay, so it is 1.11. I will go to 1.10. Here it is. So if you look in this table, page number 1.10, you will see there are certain steels which are used for shafts. Okay, so you can see here C40, or you can just go through these applications. But then I think C40, C45, and C50 are typically used for, or even C50 MN1 or onwards actually. Yeah, so C40 onwards. This is not used. So C40 to C60. Okay, so there is a shaft in every application. So out of this, any material you can use. As you go on higher side, obviously cost of material will increase. Therefore, we will try to select the carbon steel which is around say C45 or C50 typically. So let us select C45 as the material for the pinion shaft. And as I mentioned on the slide, well, here it is. We are into step number 7. PSG 1.9 will give you the okay. Can you change to next slide? Okay, so so you can play with this. There is no difficulty. Go to page number 1.9. Well, it will be here. See on this page number 1.9 here, we have selected C45 as the material. So find out tensile strength. It is between 630 to 710. So take average of this. Okay, then we have yield strength. This is ultimate tensile strength. Then we have yield strength at 36 kgf per millimeter square, which is 360 Newton per millimeter square. Okay, so write down that 360 Newton per millimeter square as the, what do you say, yield strength, SYT, or sigma y. So just note down that sigma y is equal to 360 for C45. Fine. Now, when you consider C45 material as sigma y, C45 material for the pinion shaft, and we have considered sigma y for that as 360 Newton per millimeter square. Let us assume some factor of safety of say 4. Okay, so tell me what is the sigma b value then, our design value, design sigma t. So 360 upon 4 will be 19 Newton per millimeter square. Okay, and then we will make use of this torsion equation. ds is equal to cube root of 16 mt upon pi into design shear stress. So by making use of maximum shear stress theory, we can find out what is design shear stress tau. And because we are making pinion separate from the shaft, there will be a key way. So design tau we will consider 75% of that of the maximum shear stress theory. Okay, so I'll just show in the code how we find out these things. So as I mentioned, we have selected shaft material as C45, sigma ys. Okay, that is design sigma y. Sorry, not sigma, design sigma y. It is sigma y for the shaft material is 360 Newton per millimeter square. We consider a factor of safety of 4, and therefore we come up with the design sigma t for the shaft as sigma ys upon FOS, that is 90 Newton per millimeter square. And by making use of maximum shear stress theory, okay, so last 10 minutes to go. Okay, I will just explain this part and let's see can we finish this. Okay, so design shear stress, I have multiplied by 0.75 here to accommodate the keyways, because there will be a slot made for the keyway and the material will become more weaker. Therefore 0.75 multiplier is considered for keyway. 0.5 is for on the basis of maximum shear stress theory of sigma ds. Okay, so you find out this particular magnitude of design tau as shown here, and making use of this equation, ds is equal to cube root of 16 mt upon pi into tau, find out what is the diameter of the shaft ds, and then we'll go for the next step. We will check whether it is integral construction or a separate construction. Okay, so tell me what is the magnitude of ds by using this. Okay, so are you calculating, somebody? So anybody is doing some calculations here?
4.966
millimeters or centimeters? Here, because
millimeters.
4 point, that is very small, no? I think you might have
Yes,
considered
sir.
mt in kg of centimeters.
Sorry.
You recalculate by considering mt in Newton millimeter, because shear stress tau is in Newton per millimeter square.
Yes, sir. 10.
10 Newton, 10 millimeter.
Yes, sir.
Let's see. I will calculate with my code here. See, I have considered mt1, which is now I will make use of that value of mt1 in this. Multiplier as 100 to convert kg of centimeter to Newton millimeter. Okay, and I am keying in this particular expression as it is here, 16 mt upon pi shear design shear stress, cube root of that, right? So it will print value of ds1, that is the design shaft diameter for the pinion. Okay, I think we have 6 minutes to go, so we can finish up this. Okay, so I will run this portion of the code. Okay, so constructional details I will run from here. Okay, till this particular portion. Okay, it is coming out to be 24. So this is a rounded up value, so it must be around 23, 20, something like that. Okay.
23.05, sir.
So rounded up is 24. That's fine. But somebody was getting 10. How is it that?
Sir, no.
I think you
My
might have
decimal was
committed
wrong.
mis. Yeah, yeah. Okay, fine. So shaft diameter is 24 millimeters. Now we'll find out what is the difference in dedendum diameter of the pinion, which we have calculated in the previous step, and this shaft diameter, that is 24. Okay, so just check it whether the what type of construction we are going to make use of. So here I have considered diff1, that parameter as root diameter of the pinion, that is 1 minus ds1, and I have considered ratio 1 as ds1 by 2, and here I am checking this condition, so it will print whichever is applicable. So tell me, as per your calculations, what construction we are going to consider, integral construction or the pinion is made separate from the shaft. Yeah, come on guys, just 4 minutes to go. Well, it appears that only Rohan Patkar performs the calculations.
Sep-
Yeah, tell me.
separate from shaft.
Separate from shaft because ds by 2 is larger than difference.
Sir, yeah, ds by 2 is smaller, no? If the difference is greater, then
Yeah. Then it is integral. Okay, I will just
then
run this. Let me see what my code says. Yeah, the pinion is made separate from the shaft. So here you can write, I have written only the pinion is made separate from the shaft. Instead of this, you can straight away write like this. Since df minus ds is less than ds by 2, then comma, and then you write this statement, which is in the code here. Comma, the pinion is made separate from the shaft. Fine. Okay, so we are going to make pinion separate from the shaft. So you go to the slide, previous slide here, and you draw this diagram here, which is shown on the right top corner. Okay, you need to draw a diagram. There is no need to show the dimensions here. You mention dimensions in nomenclature form, but nearby it, you just write down what are these dimensions, like root diameter df, pitch circle diameter, and what is the diameter of shaft ds. Okay, and what is the face width. Okay, once you do that, this portion of the design is complete. Now, as far as the constructional details of the gear is concerned, we will consider tomorrow because hardly 3 minutes to go. Okay, so shall I end this meeting now?
sir, if
Yeah, yeah, tell me.
df like addendum circle and diameter of shaft is greater than diameter of shaft by 2, then only we consider pinion
This,
is made separate, no?
huh? Yes.
Sir, then in PPT you have written if ds by 2 is greater than df minus ds, it is
एक minute.
supposed to be.
That may be typo. Let me see. Good, you're quite alert. That's nice. What I have written in PPT, where it is? In the,
Uh,
yeah, in the
previous
step,
slide.
no? Here it is.
Yeah, in step.
If df minus ds, this difference is less than ds by 2, then it is integral construction, no? It's correct.
Okay, yeah. No,
It is
no.
correct.
While saying, sir, you said like that only.
Maybe that might happen sometimes. That's fine.
Okay.
Yeah. So, but then PPT is correct.
Yeah. PPT is correct.
Yeah. So I will end this meeting now because it's
Okay,
hardly
sir.
1 minute to go. See you tomorrow, and we will continue with this similar methodology. We will have a single meeting and we will rejoin immediately. Okay.
Yes, sir.
Yeah. Okay. Bye
Thank you,
bye.
sir.
Okay. What has happened? Meeting is not ended. Yeah, somebody is trying to control our. Acha.